Hi folks, recently I prepared a video clip which showed the sweep operation in a generative shape design using a law which was specified by a sketch. Okay, so I had a sketch and I used it to specify the radius of the swept circle. For simplicity, I assumed that it was a circle that's being swept. There were no mathematical expressions specified in that particular law. So what I want to do today is to specify the radius according to a precise mathematical formula, which, for example, looks like that. What you see on the horizontal axis is the distance along the center line, percentage distance along the center line. So over the first 15.7% of the length, arc length along the center line, the radius grows from 2 linearly to some maximum value, and then for a portion of the arc length, about maybe 60 or 60% of it, it has a full sine wave, as you can see here, and then after 78% it stays constant. Okay, now when I do this, of course I do it in the context of a sweep operation, but later on I will create a third video which shows you if you want to create a mathematical expression in a sketch following this particular variation, how would you create that curve? But that is not the focus of this present video clip. The law operation, whether it's sketch-based or formula-based, etc., is often used and done in generative shape design because it's very convenient. So that is where I'm going to go. Okay, so let's go here. We create a part file. So Control N, P, part. Okay, right there. And then we are already in the generative shape design. What I would like to do is to create a rule which can be done, or a law which can be done either here by going to the knowledge toolbar and then going to F composite G, or you can also go to the knowledge advisor and then you can use the same thing there. Let's see now. This is law number 1. Very good. Now, what I have here is, as you can see in the drawing there, you have two variables. One is the percentage along the length of the center curve, which is real, non-dimensional really, and then the vertical axis is the radius, which I'm going to use inches for it. Okay, so that being the case, I introduce two parameters here. One of them is a length type, and the name of it, I'm going to call it big R, which is the radius. Okay, apply. All right, and then I'm going to do a new parameter of the type real. What is the real? Real. And let's see now, a new parameter of type real. I'm going to call this thing x, percentage along the arc. All right. The law must compute one and only one formal parameters. Okay, fine. All right, I don't know why I'm getting that message, but that's okay. Right. So what we're going to say is that if you look at this sketch, if x is less than 0.157, then it varies linearly according to this equation of this line. Now, I have to be blunt with you. When you are doing things like this, you may have to think about it carefully. How you're going to write it, how you're going to non-dimensionalize things. So I'm going to write it the way I did it, and then you think about it, and if you have a better way, that's fine. So if x is less than or equal to 0.157, then we're going to say the radius is equal to, now first of all, keep in mind that the radius, the unit of it must be length, so inches at some point. So I write a bunch of things here which are non-dimensional, and then I'm going to multiply it by 1 inch to turn it into whatever I have in mind. So 2 plus x divided by 0.157. This is a non-dimensional entity, and then multiply it by 1 inch. Notice what this says is that when x is 0, radius is 2. When x is 0.157, then radius is 3 inches. Okay. Else, if x is less than or equal to, let's see now, 0.785, then the radius is given by that full sine wave that you saw on the PowerPoint slide. So we're going to write it down. 2 plus sine of x, multiplied by, now notice that the argument of sine must be in degrees because my unit is in degrees, okay? So whatever I write after sine, when the parenthesis opens and the parenthesis closes, must be in degrees. So I'm going to write it like this, times parenthesis 360 degrees divided by 0.785 minus 0.157. Okay. And then we have to close it. We're going to need 4 parentheses unless I made a mistake. So multiplied by 1 inch. Now notice that 360 degrees, it's one full sine wave, and according to my drawing, that spans the interval 0.785 and 0.157. So assuming you have enough parentheses, I didn't miss anything, that should do it. Okay. Else, so if you're past 0.785 as far as x goes, the radius is constant. So the radius is equal to 3 times 1 inch. Hopefully we didn't make any mistake here. I don't know. We say okay. It looks like I'm good. Now, what I'd like to do is a sweep operation. So let's see now. There's the sweep. You can see that. There's a sweep. I want to sweep a circle. This is a circle. And the method that I'm going to use, the center and the radius. Okay. So the center is a center curve. I'm going to have to draw something here. So I'm going to cancel that. On a convenient plane, for example, on this plane, I will sketch. For now, I'm going to make a circle. I'm going to make it a line right there. Okay. I don't know what the length of it, and I don't care. In fact, I'm going to change later on change this thing to an arbitrary curve. So exit. Now we go a sweep. We do a sweep, which was right here. Circle, center and radius. So the center curve is right there, and the radius is not a constant, but it's following my law. So I click on the law. Okay. And then I say advanced, right there, and let's see, advanced, and it's right there, and this is exactly the shape that I have on my slide, right there, linear, full sine wave, and a constant, and the numbers are agreeing with what we had there. So remember, you need to create select advanced. You have to select the law that you created, and then okay. All right. So if you look at the front view, we see exactly the scenario: a linear variation as a function of arc length, linear variation, a full sine wave, and then a constant. Now, a couple of things. This thing did not have to be actually aligned. So let me go back to that sweep. Let me go to that sketch. I'm going to delete that and make it a spline. Spline right there. Exit. Well, it looks like that was too much variation. So let's go back here and let me change this thing to a different spline, a simpler one. Yeah, something like that. Exit. There. So if you look at it, at one end the radius is 2, then it's a linear variation. You can see that. This is the linear variation. Let me turn this thing around so you can see it. So it starts at 2, linear variation, then it's a full sine wave, and then it goes to a constant. Okay, now there's something that I would like to do for you, and that is in fact, let me do the following. Well, I'm going to stop here, okay, because this really describes the process of using a mathematical formulation, mathematical expression right there, write a conditional program, and then create the surface that we want. Now, what I would like to do in my final video on this topic, I'm not interested in the surface. I just want to have a curve in the space which follows this specification, okay? Because right now it's cumbersome in order to show that based on what we have done. So I'm going to stop this, and I'll do the third segment in what next. Okay, so.